All right.
So how about
Let's start. Go ahead and get your notes. Maybe let's start by maybe just some quick rehash of quiz kind of topics, okay? And then we'll get into homework questions. And I think this was on the video a little bit as well, but that was 2 years ago, and maybe emphasis be a little different, whatever, possibly. So let me just so if that was and you'd already written some of this down, don't worry right now. That's perfectly fine. But just to kind of review where we've been quickly, this was about definite integrals. All right, this was our introduction to definite integrals, and that was just this notation. Okay, and remember there were really there's really three ways that we can do this. One is by geometry. That's what we first did, and you should expect some of that on the quiz. That there'll be some lines and half circles, and you'll be able to find some areas that way. Okay. Another way is approximation. That's not really a big emphasis on this. Doesn't mean you might not have to approximate some areas a little bit, but that is something we actually will study much more in at the end of chapter 5. We'll get a lot more into approximation type techniques. And then we learned in section 5.3, and I'll come back and add that here in a minute, a third way, which is a fundamental theorem. Well, we can add it, I guess. Fundamental theorem part 2. Okay, and the fundamental theorem part 2 was the big F of B minus big F of A. And that's what you spent your time doing on the LH packet, and some in the book on 19 through 30 in that section there. So let's talk about that just a second. Definite integrals are just a number, right? Definite integrals are just a number. It's a fixed piece of area. So those are the three ways we can find it. Let's talk about the limitations of each. Number one, what's the limitation of using geometry? Might not be a geometric shape, right? It might be a parabola or an e to the x, some curve that is not a geometric type area, so you can't use that. Let's go down to the fundamental theorem part 2. What would be the limitations of using that? Sometimes functions don't have antiderivatives. We've talked about those. Or maybe you're just given a graph, okay, of a situation. Or what we haven't really gotten into, which we'll get into more later on, is maybe your function is just a table of values, some data that you've collected. And yet we want to use areas. So fundamental theorem part 2 doesn't work. So approximation then is all that's left in those cases. Okay, approximating areas. So we'll talk about why, and we'll talk more about that later on. But it's important to understand this idea of definite integrals. Okay, then we went to section 5.2. So there'll be some questions about that. So this is really 5.1 and 5.3. all right here, because that's really all section 5.3 was the fundamental theorem part 2. Now, it had other questions in the homework, but they mostly were questions that related back to section 2, which was the area function. So in section 2 is when we learned this thing. Okay, we learned about this thing here, where we had to put a t there. And this was, remember, this is a number right here. This answer is a number. This was what? This was an equation, or well, better, a function. This is a function. Now think of it this way. Think about when we did derivative. F prime of 2 is a number. It's the slope at 2. F prime of x is a function. It's the derivative function. So those were fairly simple differences there. We had f prime of 2, yeah, that's a number. You plug a 2 into the f prime function. F prime of x is the whole function. This was a little more confusing, a little more, complex. So, but it's that same analogy. So definite integrals are just a number, a fixed piece of area. An area function is an actual function. And of course, the big result in section 5.2 was the fundamental theorem part 1. Okay, the fundamental theorem part 1 said that, well, basically what it's saying in just common ordinary language. Fundamental theorem part 1. What did it say about the area function? The area function is the antiderivative. That is what fundamental theorem part 1 is all about. The area function is the antiderivative. That's what led us to fundamental theorem part 2. That we could use the antiderivative to find the area. But area function is the antiderivative. Now the way we wrote that is we wrote using derivative notation. We said if you do the derivative of the area function, then that gives you what? The original little f, but with an x in it, not a t. That's how you say that something's an antiderivative. Is you say the derivative of it gives you back what you started with. Then that thing inside the brackets must then be the antiderivative. So that's how we say it in math notation. But basically what fundamental theorem part 1 says is the area function is the antiderivative. So then you have all those questions that could be asked about that and that notation and what that, how you would work with that. Okay, so let's do, before we do the homework, let's do a problem, let's do a problem that would deal with fundamental theorem part 1. Let's just review one here. So let's say I gave you big F of x was the integral from -1 to x of 2t minus 7. This wasn't on the video, was it? Yesterday? Okay. Find a formula or an equation for big F of x. I'll give you a couple minutes to do that. That would be a question I might ask you dealing with area function and that notation and so forth. All right, so the idea would be that we do the antiderivative, right? The area function is the antiderivative. We do the antiderivative except with x's, right? Not t's. And then we have this initial condition, right? We know that big F of -1 is 0 because big F of -1 means put a -1 here, which means put a -1 here. The area from -1 to -1 we know is 0. That's one area we will always know. Now, since this is a line, if we drew it, we'd have other areas we could find. There'd be triangles and stuff like that, trapezoid. But in any function, even one that didn't have geometry in it, we would always know that one piece of area where it was 0. So now we do what? Put the -1 in for x. That's how we find c. Whenever we have c, we get c to be -8. If we have a plus c when we do our antiderivative, if we know an initial condition, we can plug that in. We can find c is -8, and we get that right there. Now, I want to show you, now that we have learned, though, section 5.3 with fundamental theorem part 2, there is another way. And I'll show you that. You may like it or you may stick with this. It doesn't matter. But this is a perfectly fine way to do it. I like thinking about it this way. I think it shows understanding of what the area function means. I think it connects back to what we did with differential equations, initial value problems, and finding the C that way and so forth. But since we learned fundamental theorem part 2, let's change to blue. Since we learned fundamental theorem part 2, we could actually treat this like it's a definite integral. And the nice thing about doing that is we wouldn't have to worry about the t and the x thing. We could just do it like we would do a definite integral. A definite integral, we would keep this variable. So I would do the antiderivative of this, which would be t squared minus 7t. Oh, I forgot. Do we worry about the c when we do the fundamental theorem? Why not? They subtract out. The c subtract out. So what I can do here is that right bracket notation we talked about the other day. I can do this antiderivative. I can put my two things here, and all I have to do is plug those in. I can do my f of b minus f of a with this, actually. And so I can plug in the x. And so look what happens. I end up with x squared minus 7x. That's for that one. And then minus, I can't forget parentheses here. And now let's plug a negative 1 in. Negative 1 squared would be 1. Minus 7 times negative 1 is negative 7. So we end up with x squared minus 7x minus a. How about that? Works kind of slick too. Okay? Fundamental theorem part 2. Antiderivative, right bracket, put in the x, put in the negative 1, subtract them. We end up at the same place. Okay? So, presented with that problem on the quiz tomorrow, you could do that either way. All right, another one I wanted to talk about real quick that's related to homework that has to do with fundamental theorem part 1 was number 48. Now that might have been in the homework yesterday, or in the video, wasn't it? You go over number 48?
Yeah.
Okay, what can you tell me? We'll see how good you did at watching the video. What did they say? What was the key to number 48? What was it about, Spencer? The order.
I was going to say,
What difference does the order make?
you can do the derivative of the antiderivative of the area function, but you can't do the antiderivative of the derivative because then it's the plus c.
Because of the plus c. I mean, you can do it,
Yeah,
but it
then
doesn't
you get
come out
plus
to
c.
be the same thing. Okay? Now, so the order you do derivative of the antiderivative or vice versa matters. That's basically what 48 is saying. Let me show you an example of another problem where that order matters. If I do the square root of x and then square it, what do I get? If I do the square root of x squared, what do I get? Not really plus or minus. Okay, let me explain this to you. It has to do with domain. It has to do with the way the original problem is written. Okay? In this problem, right here, can x be a negative? No. X cannot be negative in this problem because you can't do square root of a negative and be a real number. It'd be imaginary, but we're not in imaginary numbers here. So, square root of x could not be negative. So when we square it, we know this answer out here is positive, right? And that's good because when you square something, you should always get a positive, right? When you square something, you should always get a positive, and we know that's positive because back here when we started, x wasn't allowed to be negative. So x has to be positive, or it could be 0. Now let's look at this one. So what I thought a lot of you would say was just this. Of course, you were on to me. You knew I was up to something. So, but a lot of times people would say that that is also just x. Could x be negative in this problem? Yeah. You could take negative 3 and square it. You get 9. What's the square root of 9? 3. It's not. Now, I know some of you are thinking plus or minus, and you're mixing that up. This is plus or minus, right? When you solve that equation, you're asking what x's will work there. If I just ask you what's the square root of 9, the answer is 3, right? It's just 3, okay? But what we're saying here is if you square and then square root, you get back what you started with, and that's not true. Because if I put a negative 3 in there and square it, and then square root it, I don't get a negative 3 out. I get a positive 3 out, okay? So I don't get back what I started, I get the positive version of what I started with. So I need absolute value bars around it. So the idea there is, again, the order that I do them matters in this case. Well, that's the same thing here. So what they had said was the derivative, I'll just sloppily write this up, but they said something like this: the derivative of the antiderivative, is that equal to the antiderivative of the derivative? That's basically what that problem was. Okay, well, in this problem, let's just do it this way. This will make it easy. In this problem, what's the antiderivative of little f? Big F plus some c. So I could replace those inside brackets with that. Now, what's the derivative of big F plus c? What happens to the c? Poof. There you go. Disappears. Okay, now, in this problem, what is the antiderivative of f prime? F plus c. That is not the same as that, because when you do the antiderivative last, you get a plus c. When you do the antiderivative first and then do the derivative, the c goes away. So the order you do them matters, just like the order you do the square root and squaring matters. They do kind of cancel each other out, but there is that little bit of a technicality. So that's what 48 was about. All right, very good. So when it comes to the quiz, those kinds of things, be able to, the notation is important. The fundamental theorem part 2, which I want to get into some of those antiderivative questions you might have on some of the homework. The notation with area function and all that. Just be able to answer those kinds of questions. Okay? All right. So, with that, let's do the book first. What questions do you have in today's book assignment? 49. Yes, that would be a good one. Matter of fact, let's do that one because that relates a little bit to 48. Now, I would say to you that short-term, short-sighted, you won't have to worry about this, one like this, on tomorrow's quiz. But for the packets that we do, for the AP test, these show up, but it shows up a little differently than they worded 49, so this would be worth going through. Now, let me first start this by doing one that I have told you already will be on the quiz. And here is the one I'm talking about. This is when we did Fundamental Theorem Part 1. Let's say we had the integral from 2 to x. Let's see, what's the one I did this morning? I did ln of sine x, I think is the one. Oh, whoops. What's wrong with that? We have a t. Can't have an x there. Okay, that was bad. I mean, I did. I got like goosebumps as soon as I wrote that x. It just was weird. Okay, so got to have t's there. So if I gave you this problem, on the quiz tomorrow, you would write what? ln sine of x. That's what you would do. ln sine of x, and you'd be done, right? Because what you're doing there is the derivative of the antiderivative. So if there was, now, it's a little bit like this problem here, except we weren't doing the derivative of it, right? If we were doing, and again, you can see why you get that same thing, because if I had asked you to do the derivative of this, it would have been what? 2x minus 7. Look what we had for big F right here. Do the derivative of it. 2x minus 7, right? You do the derivative of what we had. It's 2x minus 7. Did the c matter? No, the c didn't matter. This thing down here did not matter because we do the derivative of it. The c goes away. Okay? So, but here's one where we could do the antiderivative of this, right? We know how to. On this problem, we don't know how to, and it turns out this is one that doesn't have an antiderivative. Okay? So, but it doesn't matter because whatever the antiderivative would have been, when we do the derivative, they cancel each other out, and when we do it in this order, it works fine, the c goes away, and we end up with that right there. Okay? I don't know, can you put that in the calculator? And did it do it?
Yeah. It's like little humps.
It's like what?
Oh, and you graph it.
Oh, you
I
graph.
said a graph.
Oh, I think just, yeah, okay.
You
Oh,
put-
what
you
the
can put
function
any
is.
text in it too if you want.
Yeah, I guess what I was thinking is, if you just type this in just like that, you know, the integral to the x, it'll just give you L inside x,
We wanna
just
know
like
what
that.
the graph looks like.
Okay, yeah, and the graph's kind of.
The graphs.
Okay, so that definitely could be on the quiz. All right, now, what often happens though is you get a problem like this. You don't have to write this down just yet. But on the AP test, oftentimes they will do a problem like this. Integral from 0 to x squared. They'll do something like that. And then they'll put cube root 1 plus t squared. I think this looks like 49, doesn't it? dt. Oh, well, a little bit. This problem will be on the AP test. Now, what's different there? We got an x squared up there, which seems weird. What in the world would we do with that? Well, anybody have a guess as to what you might do with that? Ignore it? Well, what did we do with this x up here? We put it in where the t was, right? So a guess might be that you would just take this x squared and put it where the t is, right? Would that be a reasonable guess? See, that'd be a reasonable guess. It would be correct up to a point, but it would be missing something. Now, let's go ahead and go with what they gave us in 49, because actually the way they worded 49 actually is a little bit more helpful than the problem I just had up there, but I'll show you why they're the same thing. So they told you that big F of x was the integral from 0 to x, am I right? Was it 0? Cube root 1 plus t squared dt, right? But then they ask you for the derivative of big F of x squared. Now, see, I think we should have been able to at least get started with this. Forget this up here. Okay, forget this part up here right now. Just look at this line here. What is the derivative of big F of x squared? Little f of x squared times the derivative of the inside. This is nothing more than a chain rule. This is a problem I could ask you back in chapter 3. And I think you should have been able to handle it. Forget this up here. If I just ask you for the derivative of big F of x squared, you do the derivative of the outside, which is little f, leave the inside alone, and you multiply by the derivative of the inside. It's just a chain rule. Okay? Now, let's think about what this is. Let's think about what derivative, or let's think about what big F of x squared really is. Big F of x squared just says put an x squared right here, which would mean put a x squared right there. So isn't what they gave us really the same as what I have back on this picture? Right here? This in here is really big F of x squared right here. So what should the answer be? It should be little f of x squared with a 2x attached on. Now where is little f in this? Where is little f in this? That's this guy in here, right? That thing is little f. So the answer, according to what we just saw here, the answer should be little f with an x squared plugged in. Oh, isn't that what we said should happen? We said this x squared should go in here, but what were we missing? We were missing the derivative of the x squared, which was the derivative of the inside. Now, why would we have thought of that? Well, here's why we would have thought of that, because what is this x right here, this x on the inside? It's that x right there. This thing up here is like the inside of the function. It's the input, right? So here's what I'd like you, hopefully, when we see this on the AP test now, you'll look at this and say, okay, wait a minute. This is just my area function, right? This is just my big F. But look what it is. It's got an x squared on the inside. So how do I do a derivative, which is what they're asking me for? How do I do a derivative with something on the inside? Oh, I just keep the inside the same, which means I plug the x squared in for the t. So I would do cube root 1 plus, what would it be? X to the 4th And then I tack on the derivative of the inside, which would be the derivative of that. Now I just realized we didn't finish this one. We shouldn't have stopped here. What's little f in this one? Little f is that. So what's little f of x squared? That means put an x squared in for the t. So this should have been cube root of 1 plus x to the 4th, and then with the 2x tacked on. So that should have been our answer to 49. But the way you'll see it from now on is going to be this, quite honestly. You're going to see that in a packet, and they're going to want to know that derivative, and what you're going to say is, oh yeah, this is like the one, this is like that freebie that Mr. Clark gave us on that quiz that one day, right? Where all we do, the derivative of the antiderivative, they cancel each other out. What do? We take this x and we put it in for that t. So what do we do on this one? Same thing. We take this x squared, we plug it in for that t. But then we also have to tack on the derivative of that thing up there. Because that thing up there is like the inside. And whenever we do the derivative and there's something on the inside, we have to tack on the derivative of the inside. Okay? So that's what is going on with a problem like that. So not going to be on the quiz tomorrow, but later on when we see that, maybe we'll remember. Okay, another one. 55. Okay, I think I remember that section. That was the one, it had an area. It had like a circle down here. And then a kind of another circle up here, a bigger circle, something like that. Was that the picture on 55? Okay. Now, here's the key to 55. They said in the directions that g of u was the integral from 1 to u of little f of x dx, right? So the important thing there is the u matches where it's supposed to be, okay? And this was the little f graph right here. And on 55, they asked for what? G prime of 4. Now, let me give you a piece of advice that I think is very important for these problems as we go forward with area functions, especially in the packets, the AP test, final, those kind of questions. When you're given this, what do you think of right away? Antiderivative. Notice, they didn't make that big G. They don't have to, right? Just because it's an antiderivative doesn't mean it has to be big F or big G. Here, little g is the antiderivative of little f, and that's fine, okay? So that's what that's saying. How do I show that that's the antiderivative? G prime is, there you go. I would like you to get in a habit, when you're given that thing up there in the blue, when you're given an area function like that you immediately write down what I wrote down. Because now what you've done is given the basis for all of your justifications in that problem. G prime is the same as F. So therefore G prime of 4 means they really want F of 4. And since this is the F graph, all we got to do is come over here, look at 4, find the Y value, and it's 2, right? And so then all of a sudden you're like, oh, that was easy. Well, yeah, but it was about notation, right? It was about understanding the notation. That's a big part of the quiz tomorrow is, this notation kind of thing. Okay? Now, what about 58 on that one? Here's the thing I want you to remember 58. Matter of fact, I probably should go back here real quick to our notes. I forgot something that we learned in section 5.1. In section 5.1, we learned a formula for average value of f of x. And that formula was the integral of f of x divided by what? B minus a. That is an important formula. You will probably have a question that deals with average value of the function. Well, what is it? All it is do the definite integral, which is what we spent a lot of our time here on today's homework, especially 19 through 30, 3 through 36, multiples 3, finding definite integrals. And then you just divide by b minus a. Okay, it was that thing we did where we guessed where the average would be of the function. and we said that rectangle area would be the same as the area under the curve. Okay, you've got to know this formula. So when we come to this problem, they're saying is the average value, it was the average value of what? What they want to know, average value of g prime from 0 to 3? Well, that would be the integral of g prime from 0 to 3 over 3 minus 0. Now, g prime is the same as what? F. So what this question really is saying is what's the area under the f graph from 0 to 3? So we would do this area, and then I think 3 is here, and so there's a little piece of area here that we just have to approximate. So how do you justify it? I think you justify it by doing this. Now, somebody in their class said they just talked about, they wrote a paragraph about areas, and I guess you could do that too, wrote a sentence or two about areas. But what would this area be? This is a radius of 1. So pi r squared, that'd be 1 pi, but it's only a half, so that'd be negative pi halves. What's that, about negative 1.57? That'd be about negative pi halves would be that area. What's this area look like here? It's about 1, maybe a little over 1. So you add on some positive area. So this is going to be like negative half divided by 3. But what are we asked here? Is it greater than? Well, no way. I mean, it's negative. So there's no way it's greater than that. So the area is, or the average value is actually negative. That's how I would want you to do it. If you see what's the average value of a function, I want you thinking of this formula in red right up here. And notice it says the average value of f. F is what goes in the integral. So when they ask me for the average value of g prime, I put g prime in the integral. Okay? All right. What else? Any on those definite integral ones? Yes. 28. What was 28? Was that the x plus 3 on the bottom? Integral from negative 2 to 5. Now, I would not put the dx up on top. I would have written that one this way, with the dx out to the side, okay? But a lot of times when there's a 1 up there, they'll put a dx up there. Some books will do that. I'd rather write it this way. Now, what you have to understand about this one is the x plus 3 is just a shift left of this graph. Okay? So what is the antiderivative of 1 over x? Remember the absolute value we talked about the other day? Did we mention that the other day? We didn't mention that the other day? Okay, remember we were looking on page 333. That's right, I think I said I would talk about it later. On page 333, it says that the antiderivative, and there's a short list of antiderivatives on page 333. And our whole goal when we do antiderivatives is to make our functions look like page 333, because that's the short list of antiderivatives you need to know. We need to know this one. The antiderivative of 1 over x is this. Now, is that a big deal for tomorrow's quiz? Like I said, they're going to stay pretty basic. Actually, that's a pretty basic one, really. We should know. I mean, the derivative of ln x is 1 over x, so that's its antiderivative. Okay? Why the bars? Well, it has to do with the same discussion we just had over here. Okay? Why the bars? Can you put a negative into the natural log function?
No.
And I hope everybody is understanding of that. Here's the natural log function. You cannot put a negative in the natural log. So let's review this. If I gave you this function here and told you to do the derivative, you would tell me what? 1 over x. Did we worry about absolute value bars? Did we worry about any of that? No. Why? Because in this function right here, the function we started with, could x be negative? No, x can't be negative. So we know x is positive. When we do the derivative, right here, we know x is going to be positive. So we know this number is always positive. Sure enough, look at the slopes. Always positive. Okay, so we didn't have to worry about that. But in this function right here, could x be negative? Yes. 1 over x, you can have a negative in the bottom of a fraction. So x could be negative here to start. So therefore, it could be negative throughout the problem. But when we do the antiderivative, we know we can't put a negative into natural log. So we have to put bars around the x to make sure that we don't try to put a negative into natural natural log. So from here on out, I don't care if you remember why or not. It'd be good if you did, but when you do the antiderivative natural log, you got to put bars around the edge. Okay? All right, so back to this one. So what's the antiderivative here of 1 over x plus 3? Natural log, absolute value of x plus 3. Because what do you do with the inside when you do a derivative? You leave the inside alone. Right? You leave the inside alone. So the antiderivative of 1 over x plus 3 is the natural log of 1 over x plus 3. Or natural log of x plus 3. We can test it. Do the derivative. Derivative of ln x plus 3 is 1 over x plus 3. Now the bars don't matter there when we do the derivative. They're just there to make sure that we keep the input of natural log positive. Now don't forget to do the right bracket then. We got -2, we got 5. So we put in the 5, we get ln 8. Now do I need the bars on that? No, 8's positive, so I don't need the bars. Minus, then I put a -2 in there. -2 plus 3 is 1. That's ln 1. On the quiz tomorrow, you will not get full credit if you leave that as your answer. It's all no calculator. What do you need to do more here? To simplify. Natural log of 1 is 0. That you need to know. Now I will let you leave that. I'm okay with that. But if you put this in your calculator, did anybody try? Just to check? What did it say? It said 3 ln 2. Which makes sense because the log rules are that when you have a power inside there, you bring it down. 8 is 2 to the 3rd power. So then you can bring the 3 down in front. I don't need you to do that. That's fine. Okay, now somebody in the other class asked, what if it would have come out ln 8 minus ln 2? You know, somewhere I guess I draw the line on what rules you got to remember and don't, you know, I mean, I'd like you to remember them all, but, you know, if it came out ln 8 minus ln 2, I would let you leave that. However, if you do it on your calculator, it's going to give you 2 ln 2. Why? Well, one reason would be we just saw that ln 8 is 3 ln 2. So 3 ln 2 minus ln 2 is 2 ln 2. Here's another reason. ln 8 minus ln 2 is ln 4. Anybody remember that rule? When you subtract 2 logs, you can divide what's inside. So that's ln 8 divided by 2. That's ln 4. Then ln 4 would be 2 squared. Bring the 2 down in front. Math is awesome. Look at
Isn't
all
that
this
awesome?
cool.
I'm getting all excited.
Okay? I know, and you got to
Now I
leave.
have to leave.
And now you
And
gotta
it's
leave.
so sad. I didn't
And
even
you're really
know-
excited.
Such a cliffhanger.
And you're really
I
excited.
really didn't know that it was getting so close to time to leave. I thought class just started.
All right. You guys will have to look. Kind of depends how far we get here. Look online what the assignment actually today. Okay? Good luck, everybody, and your
Thank you.
music, band,
Orchestra.
orchestra. They're all the same to me. But they all make music. I mean, I know you're right. They shouldn't all be the same.
One is more contest.
One is obviously.
One is obviously orchestra.
And that's
Is that
ob-
your orchestra?
Exactly. Orchestra is obviously better, guys. We overpower Alex.
Two. She stood up for you. She stood up for you earlier
Yeah,
today. though.
when the rest of your comrades turned against you, I was still on your side.
Thank you, Alex.
Betrayal is
Wow.
All right. See you guys.
See you guys. Happy weekend.
All right. You too.
You're home.
Yes. Evening, Christmas. All right. Next one. Next one. There is one.
No, I don't think so.
We like to
56.
Yeah, do 56.
56. Was that in that section where we were doing 55 and
Yeah.
58? Okay. 56. Does G have a tangent line at x equals 2? Does G have a tangent line at x equals 2? Okay. Well, let's change that question a little bit. Let's find the equation of the tangent line and see if we run into any issues. What do you need to find an equation of a tangent line, or any line for that matter? You need the slope, which would be g prime of 2, and you need, well, you don't need 2 points. If you already have the slope, you just need 1 point, right? You need the slope, and you need the point. So what we need is g prime of 2, and we need g of 2. Okay? So what would g prime of 2 be? Oh wait, g prime of 2 is the same as f of 2. F of 2, I believe, is 0. So f of 2, or g prime of 2, is 0. So the slope is 0. What's g of 2? That would be like putting a 2 right there. So that would be putting a 2 up here. Be the area from 1 to 2. That would be this area, right? Be a quarter of that circle. That circle was an area pi. So a quarter of it would be pi force negative, right? So this would be negative pi force. So does it have a tangent line? Absolutely. There's the slope of it. There's the point. If I was going to write the equation of the tangent line, I'd put a 0 there. I'd put a 2 there. I'd put a negative pi force over there. That would be the equation of that tangent line. Of course, 0 wipes all that out. It'd be horizontal. Y equals negative pi force would be the simplified version. Does G have a tangent line? Yeah, it's got a slope. Now, if the slope was undefined, then we might say no. Okay? But that could be vertical as well. All right? Again, the notation comes into play. All right. What else? Anything else? What about in the LH packet then? We do 36. 36. Now let me make a comment about 15. I think this was in the video. Wasn't there one in the video like 15? What was the secret to one like 15 where you have the integral and you have u minus 2 over square root of u? Separate. Separate. Now, this is going beyond what I will expect you to do on tomorrow. Okay? But these are the ones, when I split that apart, that would be u over a half minus 2 over u to the half. Now, when I subtract these powers, this would be u to the half minus 2u to the negative half. Now, there might be some fractions on there. I mean, what was this integral from 1 to 4? Okay? I would not give you this one on the quiz tomorrow, but I certainly might give you this one. Right there. The one in red. I may give you that one right there and tell you to do that. Okay? The whole part about splitting it up, not that that's hard or anything, but that's what we'll be practicing more and more of as we go to our gateway test next week. Okay? So you might have to do this. So what's that mean? You better be good with fractions. If you raise this up 1, it becomes what? 3 halves. When you divide by 3 halves, you get 2/3. So this would be 2/3 u to the 3 halves. Raise this up 1, what do you get? 1/2. Divide by 1/2 is timesing by 2, so that'd be 4. U to the 1/2. Right bracket, 1 and 4. Now you put a 4 in. Should you be able to do this? Yes. If you do, what's 4 to the 3 halves? The bottom number is what? The root, right? So that'd be square root of 4, which is 2. 2 cubed is 8. 8 times that is 16/3. Put a 4 in here. Square root of 4 is 2. 2 times 4 is 8. That's the first part of the fundamental theorem. Second part, we got to put in a 1. Parentheses would be pretty important here. Put a 1 in. Now that's easy. That's just 1. So that'd be 2/3 minus, and then put a 1 in here. That'd just be 4. Okay, now we got to do a little work with fractions. We can do common denominators. This would be 24/3. This over here would be 12/3. So 16/3 minus 24/3 would be negative 8/3. 2/3 minus 12/3 would be negative 10/3. Negative 8/3 plus 10/3 is 2/3. Okay, so you may have to do that. It wouldn't be, there's not a lot of that, but okay, that's again more what we'll be doing on the gateway test. but that may come up. Okay, so you said 36? What was 36? Okay, integral 3 minus x times square root of x. This is a little bit like 18. This would be the area from what to what? 0 to 3. Okay, so what do we want to do on this one? This is a lot like 18. We want to distribute that. It's kind of like the splitting apart we did on this last problem. Okay, now some people in the art class said they would bring this up as a negative power and distribute. You could do that too. Okay, I like the idea of splitting it apart, but whatever. Okay, so this is x to the 1/2, and I'm going to distribute that. So I'm going to have 0 to 3, this would be 3x to the 1/2 minus x to the what? 3/2. Okay, because this would be 1/2 plus 1 to add the power. Okay, now we do our antiderivative. So we raise that up to what? 3/2. Divide by 3/2 is 2/3. What's 2/3 times 3? 2. That'd be x to the 3/2. You may have to work that out a little bit more if you can't do that in your head. You may have to write that down. Right? If you have 3 times 2/3, that 3's cancel. All right, here we raise that up to 5/2. Divide by 5/2, that'd be 2/5. X to the 5/2, right bracket. 0 to 3. Now notice I didn't right bracket it here because I wasn't doing the antiderivative. My first step was just rewriting the integrand, the little f. So I was just rewriting that. But now I did the antiderivative. So now I have big F. And now I'm doing my right bracket. So now we put in a 3. Now this one's a little trickier because you can't do square root of 3, can you? Okay? So I'm okay on this one if you just leave this like so. Okay, that'd be the first part. Minus, now this is easy. You put in 0, you just get 0 for that one. Okay? So I would be okay with you leaving that because now you're going to get into square root of 3 and then that's cubed. And I mean, we could do it. I mean, I'm just going to make the choice right now. I'm going to let you stop there. Now, going forward, say this is on the multiple choice problem in an AP test. That wouldn't be one of the choices. Here's what you'd have had to do. So you'd have had to say, okay, that's square root of 3. Now, what's square root of 3 and you cube it? That's square root of 3 times square root of 3 times square root of 3. That's 3 square root of 3. So 3 square root of 3 times 2 is 6 square root of 3. What about this one? This would be square root of 3 to the 5th. That'd be 9 square root of 3. And then the 9 is times 2/5. That'd be what? 18/5? 18/5 square root of 3. To subtract those, I need a common denominator. So 6, I'm going to change to 30/5. Right? Wouldn't that be 6? 30/5? 30/5 minus 18/5? 12/5 square root of 3. That would be one of the choices in the multiple choice. Okay? So, should we be able to do that? Yeah, it's just algebra. But, you know, for now, if you got to that point tomorrow, if there was one with fractions and the square roots didn't come out nice like the other one, you can stop there. Okay? All right, but again, even that one, I'm not going to give you one like this, but I might give it to you like that, right? Where it's already distributed and all that, you might have to do that. But even that would be one of the hardest ones on there, right? Any of the antiderivative ones, any of the fundamental theorem part 2 stuff where you do an antiderivative, be pretty basic antiderivative. Okay? All right, any others?
Oh, 9?
9?
Yeah. It's like a 3 over x.
3 over x squared. Okay? Here's what I would tell you about that. Is you would first write that as 3x to the negative 2. You would write it like that. Now, if that was 3 over x, we would have a natural log. Right? The antiderivative of 1 over x is natural log x with the 3. But if it's x squared or something else, right? But only if it's x to the first power, then we worry about natural log. If it's other power, then you just do it like this. Okay? So now it's just your power rule. So you raise that up 1, which would be negative 1, divide by negative 1. And then your antiderivative of 1 would be x. And then you would do your 1 and your 2 from there. Okay? And even that's a little, I'm not going to, that's probably, you're not going to have one like that tomorrow. Probably. Sure. Yeah, it'd be one of the hardest ones. But that would be. Oh yeah, 21, and we were talking about that here in class a little bit, 21 and 24. Whenever you have that absolute value, just graph it first. Okay? So on 21, I would say don't even do an antiderivative. It's just 2 triangles. Right? So just do it. On 24, it's y equals x cubed in the bars. Well, here's what x cubed looks like. What's bars around it going to do? It's going to flip this part up. Okay, well now, what is this area from negative 1 to 1? Well, unfortunately, it doesn't make a triangle, but what do you know about those 2 areas? Those are the same. So what I would say, now this graph, right, because it's flipped. So what I would do is just do the integral of x cubed from 0 to 1, and then double. That's what I would do. And so now all you have to do is make that 1/4 x to the 4th from 0 to 1, get that answer, and then double. By the way, if you ever want to check those answers in that LH packet, it's this old falling apart white solution. Okay, so that's what we would do on that one. I think it comes out 1/2. I think is what the answer comes out on 24. Okay, and 21 it comes out 1, because each triangle is out. Okay, all right. Let's do this. Let's move on here to. We have enough time here where I can show you this, and then maybe give you a little bit of time, possibly to work on homework. Now, this first part I'm going to write down. You don't need to write this down. But I want to reference back, and what we're going to do is go into a little bit more difficult antiderivatives. These will definitely not be on the quiz tomorrow. Okay, but I want to go back to something I wrote here right at the beginning of the day. We started with a definite integral, which is just a number. Then we moved to an area function. It was a specific area function. We knew the c value because of that 2 down there. Okay, so now I want to rewrite that, and again, you don't have to write this down. But here's kind of the progression. If I do an integral from a to b, that is just a number. It's a piece of area. Okay, it's a piece of area. All right, and we're learning ways to find that using fundamental theorem part 2, especially which needs antiderivatives. That's why we're practicing antiderivatives. Okay, then we move to this, where we knew the number down here, but we put an x there. Of course, we had to put a t in here. And what was that? That was a function. And more importantly, it was a specific antiderivative we could find the c, right? So we knew that that was an area function. It was the antiderivative of little f, and we could find the c because of what? because that 2 down there. All right, now, here's where I want to move to. What if we didn't know either one of those 2 there? What if we said this could be any left edge? And right x could be any right edge? And let me put the little f of t dt. What would be the difference in this one compared to the middle one? We wouldn't know c. So this would also be a function. It would be what we call a general antiderivative. And it would have a plus c on it. We could not find the c. Now, it goes, and what traditionally, what has happened is, we say, well, geez, if we don't know what that is, and if we don't know what that is, and they don't matter, in other words, we can't find the c, all we're talking about is the antiderivative, then they started using the notation of an integral without anything on the integral at all, writing it just like this. And that came to mean the general antiderivative with a plus c on it. And that's the notation we'll use. This is called an indefinite integral. So if there was anything of this you wanted to write down, it might be that. But remember, this up here was called a definite integral. An indefinite integral is simply an integral sign with no numbers or anything on it. And all that is telling us to do is do the antiderivative and tack on a plus c. Now, some of you have already done that in your calculators, I think. You notice when you go on your calculator, there's 2 integral signs. There's one that has boxes for you to put numbers in, and then there's one that doesn't have any boxes, I think. Isn't there 2 of them? I think there is. And so there's the one to put numbers in if you're doing a definite integral, or if you're typing in a, kind of spelled antiderivative wrong there, anti-derived. But if we put the numbers in, we can do a definite integral, get a number answer. If we do this bottom one, we'll get an antiderivative. Now, I don't think our calculators put the plus c on for you, so you'll have to remember that. All right, so what's that mean? Well, that's what our gateway test is going to look like. The gateway test will have a few definite integrals. It's going to be mostly indefinite integrals, where we're just doing the antiderivative. All right, so let's do a real simple one. So if I gave you this problem right here and asked you what the answer to this is, you would write down, whoa, think a minute now. Not 2x. There we go.
Plus C.
Plus c. That is your answer right there. That's all it is. So an indefinite integral, an integral sign with no numbers on it, is just saying do the antiderivative and add on a plus c. It comes from this, right? This is a specific antiderivative. We can find the c, and we practiced one of those early today. We did this one. This is a specific antiderivative. We can find the c. This one is just saying just do the antiderivative and tack on a plus c. Okay? All right, so the new one we want to do today, so you did all those ones in the LH packet. Matter of fact, I guess I didn't even tell you that. No, they were all definite integrals in the LH packet. Yeah, they were all definite. Okay, so now, what we want to do today is expand our knowledge of antiderivatives a little bit. Okay, so let's do this one right here. Okay, write that one down. I think you had one like this in the home. Wasn't there a sign with a 2? Or maybe that was yesterday. Just-
29
Yeah,
Oh,
yeah. Now, what's going on? That 4 causes a little bit of an issue, right? So what do you have to do? Kick out a 1/4. That's right. Like a divide by 4. But remember, normally, now let's think about this. When we do an antiderivative, we can check it by doing the derivative. You say, well, let's see, the antiderivative of cosine should be sine. I know we leave the inside alone, okay? But if I check this, if I do the derivative of sine, it would be cosine, leave the 4x alone, but I kick out a 4, that means there should be a 4 sitting here. But there's not. So I need a 1/4, and we did these before. When we first learned antiderivatives, we talked about these. And so you need a 1/4 out there. No big deal. I mean, it's pretty easy to get that way. Okay? Where it gets more difficult is when you get one like this. We'll make it real easy. Okay? Yeah. Here, easy. Well, actually, it isn't. What would have, here, listen, what would have made this one easier? What would have made this one so we didn't even have to worry about the 1/4 kicking out? If there would have been a 4 here, then we wouldn't have even had to worry about the 1/4, because when we do the derivative, we got to kick out a 4, and that 4 already would have been there. So I say that this is an easy one. Why? So, Callan, the answer is, the answer to this is that. Now, some of you, there's several things going on here that we should talk about. First of all, some of you are looking at it and thinking, wait, there's a 2x there. Shouldn't this been like a product rule or something like that? Certainly, I could see you thinking of that. We don't have a product rule for antiderivatives. Remember, antiderivatives are simply derivatives in reverse. Now, would you say it's true that when you were doing derivative problems, your answer was messier than the original function? Usually. Sometimes real messy compared to the original function. So doesn't it make sense when we go in reverse that the answer should get simpler than the original? Not always, because sometimes the derivative looked about the same as its answer, okay? So it shouldn't be surprising that the thing in here will look messier than the answer. Sometimes the messier it is inside of there, the easier it is to do the antiderivative. This was easy because the 2x that we needed was sitting there. You know, I've told you guys, we've had this function right here before. This integral e to the x squared. I said there's no antiderivative of that. The reason is because there's no 2x sitting out there. And there needs to be. So the fact that I put a 2x out there made this a real easy one to do. Okay, and again, we can check it by just doing the derivative. Sure enough, you kick out a 2x and there it is set. All right? Now, unfortunately, they're not always going to be just 1/4, or that antiderivative is not just going to be setting them. So, what we're going to talk about right now is something called U substitution. U substitution allows us to do these chain rule problems, which, what does chain rule mean? Stuff on the inside. When we have stuff on the inside, that's where this method is going to come in handy, and that's pretty important because almost every function we deal with has something on the inside. Okay, and here's how it's going to work. Now I'm going to go ahead and do it on this one, even though we already know what the answer is. Okay, here's how U substitution works, and you're going to have just a few problems for homework. These won't be on the quiz, but just a few, and they tell you, they kind of lead you through the steps a little bit. Okay, here's how this is going to work. We're going to say, we're going to take the thing that's on the inside. Now there might come some times we do something different than this, but for right now we focus on the stuff on the inside. We look at what's on the inside and we say, okay, that's what I'm going to let u equal. I'm going to let u equal that. Now the name is u substitution. When you substitute, what you do is you take out one thing, put something else in its place. So what we're going to do is we're going to take out that x squared and we're going to put u in its place, but we're not quite ready for that yet. So I'm going to let u equal the inside stuff. Now what I need to do is a derivative. Now it's going to be important how we write this. We're not going to write it u prime. We're going to do the derivative of u with respect to x, so we're going to write it like this. We're going to write du over dx. And that is what? 2x. Okay? And then I'm going to do kind of a magic step here. I'm going to move the dx over to that other side. It's legal, and I want to keep the x's together, and I want to keep the u's together. Now, to be honest, I'm usually going to skip this step right here, because it's the same every time. We do the derivative with respect to x, and then we move the x over to the other side. So I'm usually just going to go du, and I'm going to think to myself derivative of u, and over here I'm going to go 2x dx. Some of the other classes say it's kind of like implicit differentiation. When you tack on the x prime, yeah, you can think of it that way. It's kind of similar. Okay? But if you'd rather write out this in between step, you can. But what we're doing is we're writing down our u, and then we're doing our derivative of u. Okay? And we end up with this. Now, I'm going to draw myself an arrow. I'm doing substitution, so I'm going to write a new integral. It's kind of like a basketball game where I'm going to take the u's out, and the x's are going in. No. Take the x's out, and the u's are going in. Okay? So, now what I like to do with this is I like to circle the things as I take them out, so I make sure I count for everything. Right? One time in a game last year, Coach Boyd tried to put 6 players in. We got technical. Right? So we got to count. We got to count for everybody who's that's in there. Okay? That's one of the common mistakes people make. So I like to circle things. So for example, this thing is going to get replaced and become what? If I take the x's out, that's going to be e to the u. Okay? Those two are equivalent because u and x squared are the same thing. Okay? Now, look what I got here. 2x and dx. What's 2x and dx? Look right down here. 2x dx is the same as du. So I can take these out and put du in its place. Now the du always goes at the end, so we want to put it where it belongs. Now look at that. Is that an easy one to do? That's a really easy one to do. Remember I said that our goal is to make all of our integrals look like the ones on page 333. So what u substitution is trying to trade one integral for an easier integral. That's what we're doing. Now what's the antiderivative of e to the u with respect to u? E to the u plus c. And what do you suppose our last step is? Substitute them back out. Right? In the basketball game, subs come in, and then usually a while later, they come back out. Well, same thing happens here. We're going to take the u, take it out, and we're going to put x squared back in its place, and look what we get. Our answer we had right up here. Now, that was one you might not need to do that. That was one you might have been able to just see. Like I said, they don't usually, or they're usually not that easy. Okay? Now, I'll come back to this one. I think it's still easier on this one to just kick out the 1/4. But don't write this one down, but I'll just go through it real quick. So I could have done this one. The derivative of 4x is 4, and then dx. Notice what I did there? I just skipped that in between step. Okay, I let u be the inside. Okay, I got my u and du. So now what do I got here? I got cosine u. And then, so that takes care of that. How do I get rid of the dx? How do I sub out the dx? What's dx equal to? Can I move this 4 over here? Yes, I can. I can divide that over there. So this is 1/4 du. I'd rather not write it du over 4. I'd rather write it 1/4 du. So now what? So dx can be replaced by 1/4 du. Now, I'll be honest, I would usually put the 1/4 out here, and I would put the du over there. Doesn't matter. If I got a, b, c, I can rearrange that order when I'm multiplying, because that's basically what this is. So it doesn't really matter. So now what do you got? Well, what's an antiderivative cosine? Sine with a 1/4 and a plus c. And then I take the u out and put 4x back in its place, and look what you got. So the 1/4 kind of took care of itself without having to think about kicking it out. It happened in there. Now again, I think that's too long to go through. I think you're better off if there's just a 4 in there to know you're going to kick out a 1/4. I think that's easier to do. Okay? So that'd be good if you can do that. But on these more difficult ones, it's nice to be able to do it. Okay? So that's the process. So on your homework, I'll just leave you some time here. You got about 12, 13 minutes. I want you to look at section 5.4, 1 through 9 odd. So it's only like 5 problems. And what they do is they give you an integral. They tell you what to let u equal. It's going to be pretty obvious. I think on every one of them, it's the stuff on the inside. Okay? Now as we go through next week, we'll get into some different issues and things that can happen. But I just want you to kind of understand this basic process. So your goal tomorrow, first of all, study for the quiz. Second of all, you got about 5 little problems here. They don't take very long. You get half of them done in more than 10 minutes, probably. Okay? So they give you the function. They tell you what to put in for you, and then you just go through what we just did right here.